Okay, so now I want to solve one example of this Mantissa. So you see how you can do, how we can find these kind of floating number representations in computers and how they are formed. So let's solve a quick example here. Largest find the largest and smallest positive floating number that are represented by 7 bits such that 2 bits are for the exponent and 3 for Mantissa. Okay, so let's see what it is. So as you see, this is gonna be x equals to mb e to the power e, and the sign is positive, so s is gonna be positive. And because the base here is 2, we are in a computer system, so it's gonna be m2 to the power e, where m is gonna be also positive, okay? Or let me write it down this way. I think it's better if I write it as x equals to -1 to power s, and this equals to this, where s is gonna be 0, right? Okay, so let's first find the largest. So the largest number so let me draw this. We are gonna have 1. So we have 7 bits, right? So it's gonna be 1, 2, 3, 2, 3, 4, 5, 6. Okay. So the first one is gonna be and let me do yeah, so the first one is gonna be sine. The second one is gonna be exponent sign. Third one is gonna be then the next 3 are gonna be next 2 are gonna be for the exponent. So for the exponent, I'm gonna have either 1 or it's gonna be an integer number, right? So I'm gonna have either 2 power 1, 2 power 0, and then the next are gonna be for Mantissa, where I'm gonna have 2 to the power -1, 2 to the power -2, 2 to the power -3. Okay, so this is for exponent, and this is for Mantissa. So the sign is already given to me. It's clear from the question. So it's gonna be 0. It's gonna be positive. And the exponent sign, 0 is gonna be for positive and 1 is gonna be for negative. Of course, for a largest number, the exponent sign should be positive. So I'm gonna put it to 0 here. And then I want the largest number. So the largest exponent, so it has to be 1. And also the largest mantissa is gonna be 1, 1, 1. Okay. So the number, the largest number is gonna be 0.111 in base 2 to the power 1, 1 in base 2 again. So it's gonna be what? So the mantissa is gonna be based on this formula here. So let me just do it like this. It's gonna be 2 to the power minus 1 plus 2 to the power minus 2 plus 2 to the power minus 3 times 2 to power exponent. The exponent is gonna be 2 power 1 plus 2 to power 0, which is gonna be 3. This, if you calculate it, it's gonna be 7. So 7 is the largest number that you can represent this way. And then the smallest number, you can do it yourself, so it's a practice problem at home. Do it yourself. So find the smallest number yourself. Of course, you have to change the sign of the exponent to be the smallest one, and also the mantissa and the exponent. Okay. So this was just to give you an idea how these bits, floating bits, are represented in computer when you have a floating number. Okay, so now I want to talk about arithmetic operations. How do we kind of add, subtract, or multiply or divide these floating numbers? So first I'm going to talk about addition or subtraction in computers. Okay, so say you have two numbers, r1 plus minus r2 is gonna be, their representation are gonna be m1 b to the power e1 plus minus m2 to times b, the base, to power e2. So the way we are gonna do this, and I'm gonna solve an example for you to understand, we shift the mantissa of the smallest number and add or subtract. So assuming E1 is greater than E2, so R2 is the smaller number, this is gonna be M1 plus or minus M2 times, so we are going to shift M2, the mantissa of M2, so b to the power E2 minus E1 by this much, and then multiply it by b to the power E1. So it's going to be m to power b to power E1. Okay. So let me show how this is done. For example, you have 1, 2, 3, 4, 5, 6 dot 7, and you want to add this with in the decimal base 10 base 101.7654. Okay, so we want to add these two numbers. So what are these? First, we convert this into scientific form. So it's going to be point, or this convention that we made, 0.1234 4, 5, 6, 7 times 10 to the power 6 plus 0.017654 times 10 to the power 3. Okay. So the way we are going to do, we have to make the exponent of these two the same. Okay, so these two have to be the same. So I'm gonna rewrite this term as, I'm gonna shift it 3 times for 3 digits. So it's gonna be 0.0001 0.17654 times 10 to the power 6. Okay, so now we have the same power like here. So I can factor them out and easily add them together. Okay, so it's gonna be 0.1234567 plus 0.00107654 times 10 to the power 6. Okay, so this now is pretty simple. We can just add these two numbers together. It's gonna be 0.123, and then only this one, 4 plus 1 is gonna be 5, and then the rest are similar. So we are gonna have 5, 8, 4, 6, 5, 4 times to the power 10 to the power 6. Okay. So now when you add this, as you see, the number of significant digits has increased now. So for example here, the number of significant digits were 7. So as you see, number of significant digits of Mantissa were 7, right? That we stored in the computer, say. Okay, so now this has increased to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so in the computer, we have to, if you want to save this number, and if you only have 7 bits to store this number, we have to chop the extra numbers, right? The extra digits that are less important and less significant. So this will be stored as follows if Mantissa is allowed to have 7 significant digits. So we can do two things. We can either chop it. So this is called whatever after that. So this is called rounding by chop. And the other one is we can just round it to the nearest number. So it's called round to nearest. Okay. So chopping is like you have 1, 2, 3, 4, 5, 6, 7. So we are gonna just chop whatever it is after that. So we are gonna just chop these numbers, okay, and get rid of them. So this is the chopping. So let me write, if we do chopping, what's gonna happen? It's gonna have 1, 2, 3, 5, 8, 4 times 10 to the 6. And if we do round to nearest, we are gonna round it. So for example here, as you see, after 4 we have 6. So it's closer to 5 rather than 4, right? So the round to nearest is gonna give us 1, 2, 3, 5, 8, 5 times to the 10 to the power 6. So as you see, this is closer to the real number than rounding by chop. And so rounding by to the nearest is usually more accurate. It's more accurate than rounding by chop. Okay. So here I want to define two errors. So these errors are very important and sometimes for this computation. So one is absolute error. So the absolute error of actually absolute error of this floating operation is defined as x minus floating. Floating means the floating representation of x, the number. This is going to be the absolute error of that. So here is going to be what? It's going to be if we do it, for example, for round off by nearest is going to be 0.0346 is the round off to nearest machine error. Okay. And then the other thing we have is relative error. We can define. So the relative error is defined as x, the number, minus floating x over the number itself, x. So if you don't know, so this is floating x. So I'm gonna write it as floating x by round to nearest. And this is floating x by chopping, okay? So we have to subtract the real number. So this is our x, right? So this is, for example, the x. And we have to, when we do the floating representation of that, it's going to be like this. And this is going to be the absolute error of that for let me write it down as, for example, round by nearest. And you can calculate it for round for chopping, which is going to be larger than this, okay? So here, I want to define another thing, and that is machine epsilon So machine epsilon or machine error is gonna be b the base to power 1 minus t, okay, and t is number of significant digits in Mantissa and rounding. Okay, so for example here, the epsilon, the machine epsilon for this example is gonna be 10 to power 1 minus, what is the number of the significant digits for Mantissa? Here is going to be, for example, 7, right? So it's going to be, the machine epsilon is going to be 10 to the minus 6. Okay. And we have some relations here. And the one is the absolute error so the absolute error is going to be always smaller or equal to epsilon over half times the x. Okay, so the absolute error is going to be always we are gonna have this, and the relative error is going to be always smaller than or smaller or equal to epsilon over half. Okay. So these are pretty simple, like 10 to the minus 6, if your number is, x is this, so our relative error, for example, here is gonna be always smaller than, absolute error is gonna be smaller than what? 0.123 5 8 4 6 5 4 4 6 5 4 4 6 5 4. And as you see, it is like, right, so here our absolute, so this is the maximum absolute error, right, that we can have. Correct? And this is going to happen, for example, when you subtract it, for example, your or add something as 0, right? So if it is 0, you're going to have this much absolute error. So I mean, the absolute error should be always smaller than this. So this is the maximum absolute error that can happen for this case, okay? So for example, here, as we said, this is going to be, the epsilon is going to be 10 to the minus 6. And sorry, this should be over 2. I had a mistake here. So this is gonna be the absolute error that can happen for this problem. Okay, so we cannot have any error more, absolute error more than this. Okay, that is not with zero necessarily. Okay, so the other operator that we are gonna look at is the first one was addition. The second one is multiplication and division. So we have, for example, R1 times R2 is gonna be M1, M2, B, E1 plus E2, right? So this is how we are gonna do the multiplication. So the approach is we add the exponents, we multiply Mantissa, normalize, and chop or round. So this is the general approach that we have. So for example, let's do 0.1 in base 2 multiplied by 0.1 in base 2. This is gonna be what? So I am gonna multiply the Mantissa. So Mantissa is 0.1 and add the exponents. So the exponents are 2 to power 0 for all of them, both of them. So 2 to power 0 plus 2 to power 0 is going to be 2 to power 0. So it's going to give me just 0.01 in power in base 2. And this is already normalized. And then let's look at another example for 77 in base 10 times 88 in base 10, this in the decimal. So first let's normalize them. So it's going to be 77 times 10 to the power 2. This is multiplied by 0.88 times 10 to the power 2. So I'm going to first multiply the Mantissa. So 77 by 88 is going to be 0.6776. And then I'm going to add the exponents, 2 to plus 2. So it's going to be, and then I'm going to round to Mantissa. If we have like two significant numbers, so it's going to be 0.68 by rounding, 0.68 times 10 to the 4, right? So let's now calculate those again. So the round of error. So the round of error here, absolute round of error is going to be what? Is going to be 0.6776 minus 0.68 times 10 to the power 4 is going to be 24. And chopping error is going to be, if we do just chopping, is going to be 0.6776 minus 0.67 times 10 to the power 4 is going to be 76. So chopping error is always greater or equal to round of error. Okay. So this is when you have multiplication and division. And the other thing I wanted to talk about is error propagation. And this is very important when you deal with programming, and because this is one of the important error sources in your programs. And this error propagation is for different operations that can happen. For example, for some functions, if they are ill-conditioned, this machine error can be propagated, can be amplified and magnified, and smear your solutions. But I just want to give you one example for these arithmetic operations, that how can they propagate error and magnify it. So for sum z equals to x plus y, for when x is almost equal to minus y, we are going to have subtractive contraction. And let me explain what it is. Subtractive cancellation. So suppose four significant digits. So we want to subtract 1001 from 1002, 0.00102. So as you see, we have four significant digits now. And when we do the subtraction, this is going to give me 0.1 times 10 to the power 4. Right? So let me just do something here. So this is 10 to the power 4 minus 0.001 10 to the power 4. This is going to be 0.1 times 10 to the power 4. So now we only have 1. So only one significant number. Right? So this is going to make to a subtractive cancellation, a catastrophic cancellation of the significant digits that can really smear out our solutions. So in general, I can say that we can write the error of z, a summation, a relative error. I can write it as x1 plus the relative error of x plus y 1 plus its error minus x plus y, the actual numbers. So those are the representations. So these are the floating representation of x, and this is the floating representation of y, over x plus y, right? So this is going to give me x over x plus y times error x plus y over x plus y error y. So we can say that the relative error of z, the summation, is going to be always smaller or equal to x plus y, the error, times ex plus y over x plus y ey. So if x is around minus y, then x over x plus y, this the absolute of that, and y over x plus y are gonna be very, very large number than 1, because this is gonna be around 0, right? This is gonna be around 0. So this is gonna be a very large number, and this is gonna lead to a large magnification because this is magnified, right, of relative errors. This is called sometimes catastrophic cancellation. Okay, so this was one note and remark that I wanted you to know, because this is very important, that this can lead to smearing out your results, especially because of these round-off errors that are going to happen, and this chopping that is happening in the computer. Okay, so you have to be aware of this. Study this more if you want to know more information. But this is what I think the knowledge that you need for this course. So the last thing I want to note is just introducing two terms that are important, and that is the IEEE, especially if you are doing programming, the IEEE standard for floating point arithmetic. So you might have heard like single precision or double precision, like files or computation. Okay, so IEEE has set some standard for half precision, double precision, or single precision, like arithmetic, operational arithmetic. So for example, for 32-bit, we have a binary 32. This is gonna be, we are gonna have a single precision arithmetic, and the significant digits, so the significant digits for this is gonna be 24, and the exponent digits is gonna be how much? So 24, we have 32 bits, is gonna be 8, right? So in a single precision, we are gonna have 24 Mantissa, 24 bits for Mantissa or significant digits, and 8 bits for exponent digits, okay? So for a binary 64, where we have double precision, we are gonna have 53 bits for significant digits and 11 bits for exponent digits. Okay, so this is a standard set by IEEE for these calculation and arithmetic operations of floating points. Okay, so let me review the course, what we learned today. So today we mostly talked about different error types, the round-off errors, we talked about the round-off errors, truncation errors, and other type of errors that are possible to occur when you try to solve a problem or PDE numerically. Then we talked about focus on round-off errors. We defined significant digits, number systems, integer representation in computers based on bits, floating number representation, where we first have the sign of the number, and then we have the sign of the exponent, then we have the exponent, and then we have the Mantissa part for the bits, computer bits, and then we solve some examples for that. And after that, we did some arithmetic operations. We learned how to add or subtract two numbers. So this is going to be happening with shifting the mantissa of the smallest number. And then we talked about this rounding then and chopping that might occur because of the significant digits that we have, limit that we have in storing these digits into computer. And then this is going to lead to some absolute error of floating and also a relative error of floating that we defined here. And this is also, we also said we are going to have a machine epsilon or a machine error that is always, the absolute error is going to be smaller than half of the epsilon times the number, and the relative error is going to be always smaller than the half of the machine epsilon, okay? And then we did multiplication and division, how we are going to do that. That is by adding exponent, multiplying mantissa, normalizing and chopping or rounding. And finally, we talked about error propagation, the subtractive cancellation, the thing that might happen here. And then finally, we introduced these single precision and double precision binary systems for floating point arithmetic. Okay, so in the next lecture, we are gonna talk a bit more about truncation errors and start going through the numerical solution or find a difference for partial differential equations.